In this section, I'm going to talk about GPS, or more precisely, GNSS. GNSS stands for Global Navigation Satellite System, and GPS is Global Positioning System. GPS is an American system, but there are other systems, satellite navigation systems, including the GLONASS, which is a Russian, the Galileo, which is a European Union system, and the BeiDou 2 system, which is Chinese. Each of them are equipped with 20 or more satellites, meaning that in any given time, there are at least 3 or 4 satellites above the horizon, wherever you stand in the global Earth, and then you can estimate your position using those satellites. The system of global satellite navigation is quite complicated, and it involves a lot of segments: the space segment, the satellites, the control segments. But I want to focus on the navigation. The phone has a GPS. This drone has a GPS, and it's actual not just a GPS but a GNSS. Let's look at GPS in our sensor. So a GPS is extremely common, and we see that I got here a position. My position is, 32.15 lat, and latitude is 35.102. Those are sphere coordination, or coordinates on a sphere. So an Earth is kind of a circle, a ball, a sphere, and I can think of it as the equator to be 0. Above it will be a positive number in an angle. So above the equator, this is the equator. Above that will be like, 20, 30, Israel, 50, Norvegia, whatever. And North Pole will be 90. Backwards, Australia would be negative in the north part, and New Zealand even lower, and then the South Pole will be minus 90. In terms of the x-axis, or the eastern axis, so we have the Greenwich line, which is in Britain somewhere, and if I go east, then it increases, my coordination increases. So here we are in 35 in Israel, and if I go west, so all US are in a negative number in the longitude. So in that manner, it's plus 180 and minus 180. So it's 2 pi of an angular kind of coordination system. So most of us humans are living in close proximity to the ground. The ground of the Earth as a sphere is measured with respect to the sea level. So you might live a few kilometers above sea level. We hear about 700 or 650 meters above sea level, and you may live in nearby the shore. So you are in more or less a little bit above the sea level, or you may live below sea level, like behind me, like 10 or 20 kilometers. Just behind my back is the Dead Sea in Israel, which is below 400 meters below sea level. But in perspective, most of us are more or less about 6,371 kilometers from the center of Earth, meaning we are more or less on the radius, on the boundary of a sphere or Earth. So the attitude of the GPS, so we have the X and the Y being sphere coordination, and the attitude is just the radius or the distance from the sphere. Now, the Earth is not really a circle, it's not really a ball, it's not really a sphere, it's some complicated geometric or physical planet, which called a geoid, which is the shape of Earth, but keep it simple, it's a sphere. So the attitude will be the level above sea level. The phone computes its position not necessarily using GNSS, but also using Wi-Fi or 4G, LTE, 5G networks. The idea is quite complicated, the implementation, but in general it's motivated by the following idea. If I know the closest 4G antenna that I'm connected to, and I have some other antennas that I'm connected to or detect, then I can compute some sort of triangulation and know where I am with respect to within accuracy of maybe 100 meters or so. Currently, my accuracy of the position is 280 meters, and this is because the GPS is not working now. My position is roughly estimated using 4G, and I know they should be 32 satellites in my view, but because I am in a metal building, there's none of them actually being received. If I were to go a few meters outside, or if I took the drone outside, then I can count the number of satellites. Keep in mind that in order to compute an 3D, so a latitude, altitude, longitude, and altitude of my drone, of my phone, I am only required about 4 satellites, but commonly those GNSS systems uses a way more in order to have a more accurate and actually a more robust computation. And this is done using quite involved math or engineering, but as in the case of a gyro or an accelerometer, everything is packed into a little piece of silicon and the computation is being done there. On Android, on modern Android, you now can get the raw data measurements of the GPS and the GNSS and compute it yourself or try to detect anomaly yourself. But in general, most of us use GPS or GNSS for positioning, and for that we need to have a clear line of sight to the sky, and basically that's it. Let me emphasize a few more things. GPS also allows you, or GNSS also allows you to have an accurate clock or measuring of time. There is a GPS time, a notion of a global time. So we don't have like, in GPS time, you can be in one place or another place or another continent, but the time is the same to everybody. And okay, so those system allows us to have an accurate time, accurate to the way, even more accurate than 1/1,000,000 of a second. About 10 times that accuracy we can get from a GPS. Another thing we can get from GPS is the velocity. The velocity is measured using the same satellites, but the actual parameter we use is the Doppler shift. So while computing my position, assuming I have a satellite here, and my nose is a third satellite. So the phone in my hand could compute its position using the triangulation or triangulation, which is the relative distance to those satellites. Now, if all the satellites are located just above it, then maybe the altitude will be very accurate, but the XY or the latitude, longitude might be drifting. This is the main reason we might use a lot of satellites from all around. In terms of the velocity is computed using the Doppler shift, meaning I know my rough position. I know the velocity of the satellite. I know the accurate frequency of the satellite, and I know the received signal, its accurate frequency. By using that difference between the transmitted frequency and the received frequency, the Doppler shift could be computed. Knowing the Doppler shift, I can compute my relative speed to the satellite. Doing that to few other satellites, or maybe 10 or 20 or 40, you can compute your accuracy to an extreme level, actually more than 10 times more accurate than your position. So the velocity in meters per second, say, is a way more accurate than your global positioning, which would be in meters. So in a standard GPS, we could expect an accuracy of, 2 to 5 meters, and sometimes more than that. But in terms of velocity, we are way more accurate than 1 meter per second. Actually, it's below 10 centimeters a second. I want to note a few other things. Some smartphones these days have open system or multi-channel GPS or GNSS, and some others allows computing raw data or measuring raw data, as I mentioned. And with those, you might be able to compute a more accurate position, but pushing the accuracy from, I don't know, 1.5 meter or 2 meter to few centimeters is a matter of antennas and a matter of systems, some sort of calibration system or real-time kinematics, which is out of the scope in terms of this course.